I believe we're live. Okay, so today we're going to start with mathematics for comparative programming. Okay, so let's see. I don't know why this is. Okay, I have to take care of. Anyways, let's make a new folder. Let's go back here. So today our topic for discussion is divisors, GCD LCM. Okay, this is our primary target for today. We will be dealing with other topics as well, but we will be solving a lot of Codeforces questions from 1300 to 1900 as we progress through this course. Maths is very important. I just want to say that if you want to be a good competitive programmer, you need to have a good mathematical understanding of equations, how to manipulate them, how to manipulate equations in such a way that is advantageous to you, finding integral solutions, think about integral solutions, dividing by GCD of every number, like if you are given an array, transforming that array by dividing every element by the GCD of that number, helpful. These kind of tricks we will learn in this mathematics for comparative programming course. I believe we are live. Now, wait, I don't think the internet is very good. Can I just wait a minute? Yeah, so we are back. So we were studying about this. Okay, so let's first think about divisors. Okay, so what is a divisor anyway? For example, you are given an integer a and an integer b. Okay, if if a divides b, then I know that b modulo a equal to 0, or I can write b as some p times or m times a, where m is an integer. This symbol, which is a vertical bar, is called divides. Okay, so in this case, I say that a is a divisor of b. Mm, a is a divisor of b, or a is a factor of b. Okay, or we also say that, let's make this. Okay, so if a divides b, let me just make this symbol is called divides. We call it a is a divisor of b, a is a factor of b, or I can say that yes, b modulo a is 0. So b can be written as m times a or some multiple of a. Okay. Now let's take an example. Let's say 12 is given. What are the divisors? 1 divides 12, 2 divides 12, 3 divides 12, 4 divides 12, 5 divides 12, 6 divides 12. Sorry, 5 doesn't divide 12. My mistake. 6 divides 12. 7 does not. 8 does not. 9 does not. 10 does not. 11 does not. And 12 divides 12. So these 1, 2, 3, 4, 6, 12 are called factors or divisors slash factors of 12. Okay. So now you know what is a divisor. What is this divides symbol? This is called a remainder symbol, by the way. That whenever I divide B by A, I don't get any remainder or the remainder is 0. So A completely divides B or some multiple of A is exactly B. Like, okay. So this is an example. You can take any other example. You can do it for 14, 17. You see for 17, only 1 and 17 are factors. That's why 17 is called prime because only two factors. Okay. 14 has, I think, 1, 7, 14. 2 also, 1, 2, 7, 14 are the factors. For this, it will be 1, 2, 7, 14. For this, it will be 1 and 17 only. I hope this is making sense. Okay. Now, how do we compute divisors efficiently? So let's say we are given 347 and I want also 345 and I want to compute the divisors of this number efficiently or make a computer calculate these divisors. One way is just checking that let's check for 1, let's check for 2, let's check for 3, let's check for 4 up to 345 and I can check if so I will run through this loop. So I can say that let's say this is a set and I will say I belongs to this set and I will say if let's say this is n. So if n modulo I is equal to 0, then okay, let's make a set called factors, maybe set of integer factors. Okay, now we can see the factors dot insert I. So now we will get this set. Of course, you can make this a vector or array as well. You can push it into array because none of this will repeat, you understand? Okay, so this is one way. Like you understand that this is a order n operation where n is my number. Okay, so if my number is 10 to the power 6, then I can do from 1 to 10 to the power 6, I can loop through every number and check if that number divides this. Let's say n is up to 10 to the power 6, so I can just loop from 1 to 10 to the power 6. Even for 10 to the power 7, maybe this is possible. Like in some compilers, it may fail. Let's check up to which n it's getting accepted and at what point we have to let's open a folder. Let's make a new folder called uh, maths for CP. Let's go to that. So the first part is called divisors. Okay, let's start with the basic template. So this is a very simple basic template of C++ code. Now we have mentioned that let's say we have entered a number which is n, which is 345, and we want to know if, or maybe print all the factors of this n number. Okay, and we understand that this is the order n operation where I'm looking from 1 up to n. Okay, so let's think. So I will just take an integer, take in that number, and we will look through this. So I'll start from 1 and I will go up to n. I mean, I will go less than equal to n, and I will check if n modulo I, if so, that means this means that I divides n, right? This is the checking condition. If I divides n, then I can just push it into some set or vector. I can just set of int factors, or it can be a vector of int. I can just push back. So I can just set factors dot insert. I can just insert I. Okay. In the end, we just want to print. So for, no, not for each, maybe int x through my factors. I can just see out. In the end, we can just give a line break. Okay. So let's test it for some test cases. Okay, I have to give a semicolon here. Let's create a problem. Let's say my n is 12. So you see, we have the factors 1, 2, 3, 4, 6, and 12. Let's do it for some another test case. Let's make it 345 with the test case. So we should get all the factors of 345. You see, these are the factors, or these are the numbers that divide 345 directly. I hope this is visible. Okay. Now we want to do it efficiently. Let's see up to which n this runs well. So what I will do is maybe test for different uh, limits of n. Let's try 1e5, and we will check how much time it does it take. So wait, 1, 2, 1, 2, 3, 4, 5. So 10 to the power 5. So it ran for around. Why is it not showing me the time? Oh, 33 milliseconds. So very less. Let's add one more zero. So 10 to the power 6. 1, 2, 3, 4, 5, 6. So it ran for 38 milliseconds. Still not not much. Let's try 10 to the power 7. 10, 1, 2, 3, 4, 5, 6, 7. Now it's taking some time. So 71 milliseconds. Let's try 10 to the power 8. 1, 2, 3, 4, 5, 6, 7, 8. I think some caching is going on. Otherwise, this should take at least 1 second. You see, I'm already close to half a second. So 10 to the power, I think this is 7, right? 1, 2, 3, 4, 5, 6, 7. This is 10 to the power 8, which should be around 1 second of operation. And it is, you see, it is already taking half of a second. Maybe it should take 1 second, 10 to the power 8 operations. Let's try 10 to the power 9 now. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. It should take longer now, like at least 5 seconds. Yeah, it's taking 4.5 seconds. So we understood that up to 10 to the power 7 or 8, it's acceptable if the time limit is 1 second. Okay, yeah, okay, this millisecond, you understand that 1 second is 1000 milliseconds. So this time is in milliseconds. So 4419 means around 4.5 seconds. I hope this is making sense. Okay, so up to 10 to the power 8, it's acceptable, or 10 to the power 7, it's acceptable. But what if n is up to 10 to the power 12, or 13, or 14? In that case, this will give clearly. Why I'm talking about 10 to the power 12, 10 to the power 13? Because these factors can be found more efficiently. Let's discuss that algorithm. So n is up to 10 to the power 7 or 8. It's possible. Okay. Now let's try to find it the root n way. Let's take an example to form the intuition why we are looking for root n. Let's say n is equals to 36. Let's find the answer through code. So new test case 36. So these are the factors. So I will write it down 1, 2, 3, 4, 6, 9, 12, 18, 36. Back to iPad. You understand that these factors are pairs. 1 into 36 is 36, 18 into 2 is 36, 3 into 12 is 36, 6 into 9 is 36, and 6 into 6 is itself 36. Let's take some other example. Let's say n is equals to 14. So 1, 7, and 14. 14 ones are 14. Okay, wait, this is 2 and 7 as well. And 7 twos are 14. So is it necessary for me to go all the way? I don't think so. What if I only go half? Sorry. What if I only go up to 6, which is square root of 36, by the way? What if I go up to 6 and I will find the other pair by dividing it? For example, I found 4. In order to find its pair, I will say, you know what, do 36 by 4. Or sorry, 18 by 4, or 36 by 4. 36 by 4 is 9. So I found its pair. If I want to find the pair of 3, I will do 36 by 3. And 12 3s are 36, so I will get 12. So the point I'm trying to make, let's say if this is n, 1, 2, 3, 1, 2, maybe 1, let's say A1, A2, A3, A4, dot, 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 AK are factors. I know all of these form pairs. So what is the least amount I must go in order to find the pair? I know that half of these are less than root 36. The other half will be more than root 36 because their multiplication is 36. Like if, imagine it like this, if n is equals to a into b, if this is more than n, root n, then this has to be less than root n. Otherwise, I know that root n into root n is n. If one of them is greater than root n, so this is p which is greater than root n, then this has to be less than root n. Otherwise, I will not get n. If both of them are greater than root n, I know root n into root n is n. If one of them is greater than root n, then another has to be less than root n. Otherwise, the product will not be n. I hope this is making sense. So I'm only iterating on a. So if I go up to root n, that means I will always find the next pair. Because if I am above root n and I'm finding its pair, then it will be less than root n. Then I must have already gone through it. I hope this is making sense. Let's take an example to understand it better. Let's consider a number which is, let's say, 16. Root 16 is 4. Factors of 16 are 1, 2, 4, 8, 16. Okay. Now 16 was 16, 8 was 16, and 4 4 was 16. What is the so if I travel up to 4, I will always find a pair. Because at this 4, if I go 5, if I go up to 5, then or 5, so I know that 16 by 5 is less than 4, right? Then it should have come here if there was a factor. Like 5 3 is a 15, 3 point something. So it should have come here. I should have already came across it if I'm going above this range to find something and its pair. So anything in this range, its pair will be in this range. So for n, like 1 something, then up to root n, and then root n is its own pair, and then some bigger value, and then n. This is roughly what the sequence should look like. Of course, n will not always be a perfect square root. Let's take an example where it's not a perfect square root. Say 15, for example. What is root of 15? I know 3 3s are 9 and 4 4s are 16. So 3 point something. I am claiming that if I go up to 3, I am sufficient. For example, so these are the factors 1, 3, 5, and 15. No other factors. So you see that up to 3, these are forming pairs. Let's take 4. Why did I not take 4? I know 15 by 4 is 3 point something. Or but 3 point something. So 4 was not required. Yeah, there was something here, but was it necessary? No. Let's take 18, for example. So what is root 18? It's 4 point something. So 1, 2, 3, 4. No, 4 doesn't divide actually. So 9, 18. So 18 was 18, 9 2 are 18, and 6, 3 6 are 18. So 18 by 4 is around 4 point something. So if I go up to 4, it's sufficient for me. Of course, 4 will not result to me give me any pair or result because 4 doesn't divide 15. But it's always less than equal to root n. It's sufficient always. If it's a perfect square, I need that root n. If it is not a perfect square, I don't need. You can try many examples. Basically, my claim is that if n is a number and one factor is greater than root and one factor is greater than root n, then the other factor will be less than root n. Okay, will be less than root n. Okay, n be a number. Hope this is making sense. Okay, so this is the logic that we will use, and that will help us tackle numbers up to 10 to the power 12, 10 to the power 13. So let's try to code this. So I will name this file as Divisors optimized. What is the difference we will do? We will not go up to n, we will go up to root n, or I can just say I star I, or square of I should be less than equal to n. This is a trick. We don't find the root, we just say. And if n modulo I is 0, then I is an answer. And we say that if What's the other pair? It should be n by I. So if n divided by I is not equal to I, then that is also an answer. So factors dot insert n by I. Okay, so that's it. Just try to take test cases bigger than 10 to the power 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this will take not a lot of time. Okay, it's taking some time, maybe too much time. Let's reduce some digits. Okay, so it's a 1, 2, 3, 4, 5, 6, 7, 8. Let's say 9, 10, 11, 12, up to 10 to the power 12. Okay, it's timed out, so it has run for 10 seconds already. Let's see if we have done any mistake. Let's take 10 to the power 12 directly. So 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, wait, 10 to the power 12, will it fit in an integer? I don't think so. So maybe LL will be required. LL. So I will just say that int has defined LL as long long. That's why it's probably giving some bad output. Yeah, you see, it only took 43 milliseconds. It was a overflow issue, nothing else. I hope this is making sense. It was timing out because probably due to overflow, maybe it was getting to some negative number. Okay, you see, up to 10 to the power 12, let's take 10 to the power 14. So root n will be 10 to the power 7 then. You see, it's still taking only 133 milliseconds, so less than half a second. So up to 10 to the power 16 I can try. 14, 15, 16. It will still be less than a second. You see, it's taking 1 second now. So up to 10 to the power 8 operations I can do. So you see, this is a big limit on which I can find every factor. Okay, so we have learned about factors. Now there is a problem of counting the number of factors. No, we don't want the factors. We just want to count them. One way is just generating the set and counting how many elements are there in the set or size of the set. The other way is doing a prime factorization and then doing something. Next topic that I will teach you is called prime factorization. Let's go back to Alpine. Wait, it has disconnected. We have a chat. Thank you very much. Can I just love? Okay. So we have understood how to find the divisors of a number in root n time complexity. Now we will study about prime factorization. Let's see. Let me just restart this. Stop it and then start it. Let's try to think about prime factorization when this iPad, as the iPad connects. So let's think about prime factorization sometime. So I make a new file called prime factorization. Now, what is a prime factorization? Hmm, hmm. For example, let's say you are given a number 12. Now the prime factorization will be that I will try to divide it by the lowest prime factor that is available to me. So it will be 2. If I divide the 12 by 2, I will get 6. Then I will again try to beat it with the or divide it with the lowest prime factor. So again 2 into 2 into 3. So this is called a prime factorization of a number. Now how can we calculate that? So we will try to find the divisor or find a prime factor, so basically smallest prime factor, and then keep on dividing it as long as it is divisible. So for every number, I must know what is the smallest prime number that divides it. Okay, that helps me out a little bit. But how do we know the smallest prime factor? One way is just up to n, calculate every prime number. Then every time iterate through it in order to find the first prime number that divides it. That's one way. Other way would be generating primes up to n. So what we can do is, let's say I'm given a number 12. So I will generate all the primes up to 12. So that will be 2, 3, let me just, okay. I don't know, for some reason this, uh, I think we do have some issues. Yeah, it's working now. Just give me a minute. Let me take a 5-minute break. We are back. Thank you for waiting for the break. So we were on the fact that we were trying to find the prime factorization of a number. A number. Okay. So I hope my audio and video is fine. Uh, so we are trying to find the prime factorization of a number. Now, how can we achieve that? Let's just say n is equals to 12. Like there is a high school standard way. So 12 we divide it by 2, we get 6, we divide it by 2, we get 3, we get divided by 3 until we get a 1. So now this requires me finding prime numbers or the smallest prime number that divides n. But in order to find the smallest prime number, I should have an idea of prime number at least. So how can we find prime numbers or generate prime numbers? So for that, let's try to first, given a number n, let's check if it is prime or not. So what we will do is, for prime factorization, at first step is try to find prime, if prime. So if prime dot cpp, let's have a basic template. So let's say I'm given an integer n, but I want to know if that is prime or not. Let's take long this time because we will be dealing with big numbers. And let's take this input and we want to know if n is prime. So that's why I did the divisors first part first. So you understand that the number is prime if the number of factors is exactly equal to 2. So we will do the similar game here. So we need this define. So if n is prime, so you know what we will do? So for, I will just say start from the first integer and then go up to root n or I star I is less than equal to n maybe. And even if I find one person, let's start from 2. If I find at even if one factor I find, that means it's not prime. So I'm starting from 2 deliberately because 1 will always divide and n will always divide. And I know that root n is at least less than n. So in between, if I even find a single factor or a pair, then it's not a prime. So I will just say if modulo I equal to 0, then I can just say not prime. Otherwise, we are confident. And after this, we can just return and or we can just say return 0 from here because we are inside the main function. Otherwise, we can just say that cout prime. Okay. So why we are starting with 2? Let's understand this. For example, n is given as 12. Root of 12 is around 3, 3 point something. So we are starting at 2, we'll go up to 3. If we find something, so 2 divides 12, which is not some other than 1 and 12. So 12 is not a prime. What about 17? We'll start at 2. Root of 17 is around 4. So 2, 3, 4. None of these divide. Now, is it sufficient? What about 5, 6, 7, 8, 9? What did they divide? Now, my question is if any of those people divide, then they must have paired with one of these, right? Like factors always exist in pairs. This part I want you to understand. For example, let's take this simple example of maybe 19 is an example. So I know that root 19 is approximately 4, 4 point something. So I'm saying start from 2, go up to 4. What are the factors of 19? 1 and 19 only. So 2, 3, 4, if cannot find, there will not be any other number. Because if there were other number, they should have paired with 4. Because 4 is approximately root 19. I hope this is making sense. So root 19 is somewhere here. And I know that factors exist in pairs. So we will say if I find even one person here, that means I am doomed or it's not a prime number. Let's check for 12. So 1, 2, 3, 4, 6, 12. And root 12 is around 3. You see, these two are forming pairs. So even if I find one person less than equal to root n, I'm sure it's not prime. Okay, so, so this algorithm runs in root n time complexity for finding prime. Of course, there is a brute force way. Check every number from 1 to n and check if the number of people who has divided is equal to 2 or not. And since we are familiar with this divisors optimized version, how to check for factors in root n time, it's helpful to find if a number is prime in root n time complexity. Let's test this. Let's input 17. It's saying it's prime. Let's check for 16. It's not a prime number. Okay. So we have found how to, we have learned how to find divisors in optimized fashion. We have found out how to check the number. But our original problem was prime factorization. And using prime factorization, we will find out the number of factors. In order to find prime factorization, we have learned about how to create primes. Now I will teach you how to generate these primes from some range to some range. Assume that let's say n is up to 10 to the power 12. So 10 to the power 12. If this is the case, and I want to check if some primes divide this number so that while staying in the root n time complexity, I can maybe find the factors. Okay. For that, I need prime numbers from 1 to at least root n, which is 10 to the power 6 in our case. So 10 is up to 10 to the power 12. I need at least prime numbers of 10 to the power 6 in order to use that fact and maybe pair it up to find out how many factors or find factors in order to perform prime factorization, of course. For example, let's say I'm given a number 243 and I want to do its prime factorization. So I need the smallest prime factor that divides this. And as long as it's divisible by some prime, it will be in pairs. One will be less than root n or equal to root n, and the other one will be greater than root n. Either it's root n into root n, or one factor is less than root n, the other factor is greater than root n. I hope this is making sense. So I need at least prime numbers up to root n. Okay. So if n is up to 10 to the power 12, I need at least prime numbers up to 10 to the power 6 so that I can use that and maybe divide the number by it and find the prime factorization somehow. Just think about the big picture. Let's take a smaller number for better understanding. Let's say 12. So I want to know the prime factorization of 12. So what will I do? That means I need prime numbers up to 3 at least. So which is 2 and 3. These much of prime numbers I require, because using these prime numbers I can maybe find out other people. For example, I found out the prime number 3, 2. So I will divide it by 2 continuously as long as it's available. So 12 by 2 is 6. 6 by 2 is 3. Again, 3 is available to me. Now, you may think, will I not require bigger numbers? Let's take a number 17, which is a prime. I know the factors are only 1 and 70. So prime numbers up to root and 70 is nothing. So in the end, I have 17 itself. So whatever is left is my answer. That's the prime factorization. Okay. Let's check it for some other numbers as well. That why am I saying that prime numbers up to root n is enough? Why not more? Let's take the number 23, for example, or 24, for example. So I know the factors are 1, 2, 3, 4, 6, 8, 12, and 24. Now, root of 24 is around 5 point something. So I'm saying that prime numbers up to this is enough, which is 2 and 3 in our case. What about the prime factors after this? Not required. Let's take 35 to prove my point, because there is a 7 prime here. So let's try to do it that way. 35, I know the factors are 1, 5, 7, 35. Now I'm saying that this up to root 35 is around 6 or 5 point something. So I'm saying 5 is enough. So I divide by 5 continuously. So I get 7 in the end. The question is 7 my answer? What if 35 into 7 was my answer? That was my question. Then you would have 2. My observation is, given a number n, if it is divisible by some prime, that prime will always be less than root n. Or otherwise, if there exists no prime number less than root n to divide it, then the number itself is a prime. That's my claim. Let's try to prove that claim. So my claim is, if n is composite, we'll do it for the prime number as well, then there exists some number prime less than equal to square root of n, such that p divides n. That's my claim. If n is composite. If n is prime, then it's itself a prime. So there exists no prime number. So then the answer is itself. It's just the prime factorization itself. So proving this is sufficient, that if n is composite, then there exists some prime less than equal to root n, such that p divides n. Let's take some composite numbers: 15, 24, 25, 27. So 15, you see, 3 divides 15. 24, you see, 2 divides 24. Let's take 35. 5 divides 35, which is less than root n. Okay? You can take any number which is composite, and you will always find some prime less than equal to root n that divides it. Why? I have already proven that given an n, there always exists some factor less than equal to root n. Now, if some factor always exists less than root n, will there not be a number smaller than that? So either that factor can be a prime factor less than equal to root n. And if it is not a prime factor, then it will be divisible by some prime, and that will be less than that. So my proof is proof. We have proved by intuition that n, if known, there always exists some factor f less than equal to root n if n is composite. Otherwise, how will there be a factor? This is there exists sign, by the way. Now, first case is f is prime. Then we've already found the answer. If f is not a prime, so f is composite. That means there exists some number less than root f. That means there exists some number p less than equal to root f such that p divides f, or let's say g, maybe g which is less than equal to root f, and g divides f. Let's make it such that like this. Otherwise, it will get confused with the such divide sign. Now again, g can be a prime. Then we have already found our answer recursively. Or there, if g is not a prime, then there exists again some factor less than root g. So you understand, at some point I will reach a prime. And then we can backtrack inductively in order to say there always exists a prime less than equal to root n if n is composite. I hope you understood the proof. This is a very intuitive proof that there always exists some prime factor less than equal to root n if n is composite. If n is prime, it's a prime itself, already an element of prime factorization. No need to break it further, like in the case of primes, of course. Okay. Now we have proven that this up to root n is sufficient calculation of prime. Now I want to find all the, or maybe count all the divisors. Now we will try to generate prime. Now we have proved that prime numbers up to root n generation is sufficient in order to find every pair of factor, or maybe every pair of prime factor or something, or maybe do a prime factorization. Basically, we have proven that given an integer n, if we have prime numbers up to root n, we can do the prime factorization. That I will always find the number and I will reduce it continuously, logarithmically, by division. Okay, so let's try to generate primes now. So now we will learn Now we will learn how to generate primes up to n. Like, let's consider the root n to be n. Let's say I want to generate, if n is up to 10 to the power 12, we want to generate primes up to 10 to the power 6. So we will learn how to generate primes up to some given number n in order to perform prime factorization. Okay, so there are two ways. One, I want to generate primes up to n. There is of course an n root n solution. Like I will go to every number and I will ask, is it prime? And the function is prime takes root n time complexity, as you can see in this question or in this code. This tells me if it is prime or not. So in order to tell if a number is prime, I can do it in root n. In order to generate prime numbers from 1 to n, for every number I can ask, are you prime? If it is a prime, let's push it into some prime or prime number factor or prime number array or some prime number set. Or I can just make an array, and if it is a prime, at that position I can mark it as 1. So 10 to the power 6 size array. At position or index 2, I will mark it as 1. Index 3, I will mark it as 1. Index 4, it will remain as 0. I hope it's making sense. Let's write down the code. Generate primes. So basic. So we know is prime function from this here. Given an n, I know if it is prime or not. I will just use this. And I will make it a Boolean function. Okay, so I think I've done a spelling mistake. Generate, Generate. Okay, now we are on generate primes. Now we want to generate primes up to n. So maybe I will take in LLN as input. Now I want to check. So I will just say, not for int I equal to, or let's say n is equal to 0, n is less than capital. So let's make this capital N, and I want to generate primes up to capital N. And then small n plus. So what we have done? Okay, I need this long definition. So we have taken a big integer n, and for every n from 1 to n, I'm asking that let's let that loop from 2 to n and check if it is a prime or not. So if n modulo I equal to 0, I know it's not a prime. So let's make a vector. Let's make it Boolean, because if it is a 0, it's not a prime of size capital N. So if I have found something, then I know that n is not a prime. Initially, I will mark all of them as true. And I will say that n has been declared as non-prime. So I will just say that prime of n must be false or false. Otherwise, prime of n, if it is not proven to be true, so it's already proven or it is already declared as true. So what we are doing is, given a big integer n, I'm iterating from 1 up to n, and for every integer I, I'm starting from 2 up to root of that number and checking if that number is prime or not. So let's test this. Let's try to generate primes up to 20. Okay, of course I need to prime. Put this int x through prime, not actually bool, or I can just iterate through this. N is less than n. So I will set if prime of n equal to true. So it's a prime. So I will just print that n is okay prime, and we'll just say slash. Otherwise, we will print is not a prime. Let's put it into else block. Let's try to print this now. Okay, one is a prime. Okay, I have to mark that one as not prime because one is not considered prime or composite anyways. So you see 2 is prime, 3 is prime, 4 is not prime, 5 is a prime, 6 is not prime, 7 is a prime. You see up to 20 we have generated all the primes. The question is up to which this will work. Will it work up to 10 to the power 3? Yes, 10 to the power 3 into root of 10 to the power 3. So it's around 10 to the power 5. Now what about 10 to the power 6? 10 to the power 6 into root of 10 to the power 6, which is 10 to the power 9. So it may fail in 10 to the power 6. So n up to 10 to the power 5 will work. But there is a better solution. Our solution is n root n. There is a solution that works in n log log n. That's called the sieve of Eratosthenes or Eratosthenes or something. I'm sorry if I'm pronouncing it wrong. Okay. Wait, it got disconnected again. Come on. Every time is an issue. So what we're saying is if so this will work up to 10 to the power 5. Let's check it for 10 to the power 5. So 1, 2, 3, 4, 5. Of course, printing takes a lot of time, but you see that 1 is a prime, 2 is prime, up to a lot of integers. It has said that if it is prime or not. Now, after a point, it has stopped printing because out of number of characters allowed to print at a time. But this will not be a problem in Codeforces, of course. Just exit this. Okay, so let's try to print it in the normal terminal. So let's print n is equals to 1, 2, 3, 4, 5. Now see, it's printing. It will take a lot of time because it's 14,000, 15,000, 20,000. Since it's a long output, it will take some time. But if you just cancel it, you will see that 35,831 is a prime. Okay. Now we have learned that how to generate this in n root n time complexity. The question is, can we do it faster? Uh, so what we will do is, I will play a trick, basically destruction trick. Basically, what I will try to do is for every prime I find, I will mark all the multiples of that number as not prime. For example, I found out 2 is the prime. Then I will mark 4, 6, 8, 10, 12 as not prime. So let's make a copy of this. Generate primes optimized. Okay, so let's think about it. So initially I will mark everything as not prime. Now I will not prime. So, and I will say that prime of 0 equal to prime of 1 equal to false. That that 0 and 1 are not prime. Because if 1 is prime, then it will just do everything. It will just mark everything else in the world as not prime. Okay. Only primes are allowed to mark the multiples of prime as not prime. So what I will do is, initially I will just loop through it. So for int n is equal to 2, n is less than equal to n, which up to which I am trying to generate primes, I will check if this prime of n, if n is prime, I will mark every multiple of n to be not prime. Okay, so I will go for int n. So I will start from 2 into I, 2 into n, I less than equal to capital N, and I plus plus, and I will say prime of I equals to false. So what we have done is, if n is found to be prime, so I will go 2 into that, then 3 into that, 4 into that. I should not do I plus equal to plus plus. I should do I plus equal to n. So first it will be, it will start at 2 times n, then it will go 3 times n, So I must add n more to it. For example, 2 is proven to be prime. So what it will do, it will just go to 4. So 2 into 2, 4. Then it must go to 6. So it should be incremented by that number itself, which has been proven to be not prime. Sorry, prime, of course. Okay. Install this service. Try to think about this a little bit. I'm giving you and try to dry run this for 7 or 8 examples. I'm giving you 5 minutes break. Okay. Okay. We are back. So let's try to understand this sieve of Eratosthenes or Eratosthene that helps me do it in much less time. So what we are doing is, initially I just made an array of size n, 0, 1, 2, 3, dot, 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 up to n. And I say that everyone is a not prime. So composite, 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 composite. In the end, up to composite. Basically 0. 0 means composite. So that's what we have done. So we have some, uh, initially, none of them are, uh, all of them are considered to be prime. Sorry, not composite. All of them are considered to be prime by the way, because we will be cancelling non-primes. My mistake. So all of them are first considered to be primes. So 1. Then I say 0 is not a prime, goes to false or 0. and prime of 1 is false. So these two are marked as false, so not prime. Now I will start a loop from 2, and 2 is a prime. So if 2 is prime, I must go to every multiple of 2 and mark them as not prime. So we have done for I equal to 2, I less than n, I plus plus. I'm just asking if I or prime of I, if it is proven to be a prime, true, go to every multiple of I and mark it false. Okay. So what I will do, let's take this big array. So 1, let's do it up to 20 so that it's so just give me a minute. 2, 3, 4, 5, 6, 7. 30. So let's do it up to 30. I will take some colors, of course. Let's take some colors. I will say that red means prime, and green means not prime. Let's take green. Green means, or light green maybe, means not prime. Initially, everything is marked as prime. So everything is red. What was the color? I think this was the color. Yeah. Now let's make this bigger. Everything is prime. Okay. Now, after saying everything is prime, I'm saying 0 and 1 are not prime. They are composite. So what we have done, let's, why is it, can I not do it? Okay. So I've started. So 0, or sorry, there is a 0 as well. So 0 and 1 are not prime. Let's mark it as 0. 0 and 1 are not prime. Now, this is by the way a 31 size array now. Now I will say, let's go to every person. So 2 has proven to be prime. Now let's go to every multiple of 2. That is 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 30, 28, 26, and mark them as not prime. Okay. Now I come to 3 and go to every multiple of 3. That is 6, 9, 15, 21, 27. Okay. Next I go to 5 and mark every multiple of 5. So anything left? Like 25 is left, I think. Then I go to 7, mark every multiple of 7. 14 is already marked. So 7th is a 21, 7th is a 28, marked already. 11, 11 to the 22, already marked. 13, 13 to the 26, already marked. 17, 17 to the 34, out of range. 19, 19 to the 36. 38 out of range. 23 is proven to be prime, so 46 out of range. 29, so 29 to 0, 29 to 0 is 50, 58. So 58 is again out of range. So you see, in the end, whatever is left are the primes. So this is how sieve of Eratosthenes works. Now there is an optimization on this. I've started from 2i. If 2 is proven to be prime, I'm starting from 2 multiplied by I. Actually, I can start from I square. Tell you, I will explain you why. Uh, so I've said that, okay, I is a prime. So mark every multiple of I as not prime. That's my objective, right? This is my objective. I hope the stream is running well. Okay. So this is my objective. Now, my claim, no need to start from 2i. By the way, starting from 2i is also very fast. I can start from I into I. Question is why? Now, I know that 2 will mark 4, 6, 8, 10, 12, right? All of these will be marked as, okay? All of these will be marked as not prime or green. Now, 3 can start from 9. From 3 into 3, which is 9. Why? Now, I know that I is prime. So I can start from 2 into I, 3 into I, 4 into I, 5 into I. Can start anywhere. Now, if I know that anything less than I is already covered, for example, if I could have started from 2 into 3 for 3. So, okay, 3 is prime. So let's start from 2 into 3. Or understand? But 2 has already covered 2 into 3. Has it not? Let's take 23, for example. 23 is a prime number. I hope it is. Let's check. Yes, 23 is a prime number. Now I can start from 23 into 2, right? So 23 is prime. Now I can start from 23 into 2, not an issue. But don't you think the 2 has covered this 23? Like, while 2 has been proven to be prime and 2 is scanning 2 into 2, 2 into 3, 2 into 4. Don't you think it has covered 2 into 23 as well? Okay, let's not start with 23 into 2. Let's start with 23 into 3. Don't you think 3 has covered it? 23 into 4. This must have been covered by 2 already. 23 into 5. 5 has covered it. 23 into 6. 2 has covered it. So 23 into 23 is ideally where I should start. Even 23 to 22, 11 has covered it. Maybe 2 has covered it, right? So I, if prime, any value less than I must have been covered previously. So the change that I will make here, I don't need to start from 2 into n if n is proven to be prime. I can start from n into n. And I can go up to n, and I can do I plus equal to n. Let's run this for 35. So you see, 1 is not a prime, 2 is a prime, 3 is a prime, 4 is not a prime, 5 is a prime. You see, up to 35, and the 31 is a prime, 29 is a prime, 23 is a prime. You see, it's working. This is called a sieve of Eratosthenes field. So what we have learned, recap, divisors, how to generate divisors, how to uh, find if a number is prime in root n complexity, how to generate primes from 1 to n using sieve of Eratosthenes. So let's go back. So we have learned about divisors, what is a divisor, how to find factors in root and time complexity, understood how factors form pairs. We have understood how to find primes. We'll of course start with the prime factorization of a number. Knowing primes are already generated, I'll tell you how to do that. There is a very efficient way of doing that. We have learned about primes, how there's a factors, how prime numbers up to root n is sufficient in order to do prime factorization. That we have proven recursively. Okay, we have learned how to generate primes in n log n time complexity. I will tell you how. You don't have to know that why this sieve of Eratosthenes takes n log n time complexity. Just know that this algorithm, which is shown here, mm, all of these codes will be available, by the way. This algorithm that is shown here is of n log n time complexity. It's very fast. It's almost close to n. Okay. Okay. So we have learned about how to generate primes from 1 to n very efficiently. Next, we will try to form this sieve. I have already formed this sieve, by the way. Next, we will try to form a similar array that will store the smallest prime factor of an element. So if it is a prime number, I know that the smallest prime number that divides it is the number itself. If it is not a prime, like for example, 2 is marking at 4, 6. So at position 4, it should store 2. So if somebody is querying for 2, I should know that the smallest prime number that divides 4 is 2. So we will use that smallest prime factor array in order to generate this prime factorization. So this is a homework for you. Try to understand how I can form this smallest prime factor array. So basically at every position of the array, SPF of I will store the smallest prime factor that divides I. Try to form it. It will be formed similarly as the prime sieve is formed or prime array is formed. And try to think about how you can use that, the, the fact that the smallest prime factor that divides a particular number is x, how you can use that in order to generate prime factorization or, or form this prime factorization. We will be solving that in our next class, but try to think how we can do that. I think the stream is running for long enough, 1 hour 43 minutes. I will be ending the stream now. Thank you very much for watching. Like, share, subscribe if you find value in this channel. And you can support me, by the way. It's in the description how you can do that. Have a great day and keep learning. Okay, this camera was not visible.